In this chapter, we will study atomic physics, which is basically the study of building block of matter known as atom. The idea of atom has been around for a long time, about 5th century BCE. It was independently thought of in ancient civilizations in Greece, India, and China. In the modern period, the first evidence of atom was found in what's called Brownian motion. Brownian motion is a motion where if you have particles suspended in a fluid, whether a gas or a liquid, then these particles undergo complex motion as they collide with atoms and molecules of the medium. You might have seen instances of Brownian motion if you look at sunlight coming through windows of a room, and if there is any dust in the room, you can see particles of dust just dancing around randomly. So that's an example of Brownian motion. The mathematical analysis of Brownian motion allows us to figure out the size of atoms and molecules, and this was first done by Albert Einstein. Now, there have been different conceptions of what an atom looks like. What does it consist of? Rutherford's planetary model proposes that there is a positively charged nucleus at the center of the atom. It's very small in size and is very dense. The surrounding space, the space surrounding the nucleus, is very sparse. It has electrons which are well separated from each other and the nucleus. So most of the mass of the atom is concentrated in the center, in the nucleus. The rest of the atom is mostly empty space, but in that empty space are electrons orbiting around the nucleus like planets orbit around the sun. There were some issues, some problems with the Rutherford's planetary model. One, and the most important one, is in classical electromagnetic theory, if you have a charged particle which is undergoing acceleration, then it is supposed to radiate electromagnetic wave. And when it does so, it loses energy. So in an atom, if you have electrons orbiting around the nucleus, they're going around circular paths. Even if they're going at constant speed, they are constantly accelerating because they're changing the direction of their motion. And therefore, as they go around these orbits, they should be losing energy. And as they lose energy, they should spiral into the nucleus itself. Because remember, the nucleus is positively charged, the electrons are negatively charged. So there's an inherent force of attraction between the two. So if you go by classical physics, then the atoms should not even exist. Within a very tiny fraction of a second, all of the electrons would end up in the nucleus. So to get around this problem with the Rutherford's model, Niels Bohr, a Danish physicist, proposed his theory of hydrogen atom. The reason why he looked at hydrogen is because that's the simplest atom that we know. Basically, one proton in the nucleus and one electron orbiting around the nucleus. To get to further details about Bohr's theory, let's begin by considering what's called a discharge tube. A discharge tube is basically a glass tube on which the two ends of which we have a positively charged or a, 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 a metal plate, which is at a higher potential. On the other end is a metal plate at a lower potential. So these are connected to some sort of a power source, a very high voltage battery. So when the electric field set up by these anodes and cathodes is strong enough, it can ionize the molecules of the gas in the discharge tube. So discharge tube is filled with uh, a gas, and the molecules can be ionized, meaning the electrons in these atoms that make up the molecules can be stripped away, leaving behind positive ions. So once you have a large enough potential difference, you ionize the gas, and then the ions that are formed, positive and negative ions, they accelerate towards the anode and the cathode. The positive ions would accelerate towards the lower potential end, and the negative ions will accelerate towards the higher potential end. This is called an electric discharge. This ionization and the subsequent movement of the ions in the tube is called an electric discharge. During this discharge, light is emitted, which contains discrete frequencies. So if you analyze this light, it doesn't have, it's not like sunlight where you have all possible visible frequencies. The discharged light has discrete frequencies, which are characteristic of the gaseous element. So depending on what element you have in this discharge tube, you will find light of different frequencies. And by looking at that spectrum, one is able to identify what gas must be in that discharge tube. So it's like a signature. That spectrum is like a signature of an element, of a gaseous element. An example of a discharge spectrum is here. So this is the color spectrum that you see here. As you can see, it has consists of lines. So essentially, you don't see a continuous spectrum. What you see is discrete spectra. And this is from a discharge tube filled with iron ions, iron molecules. So, and the location of these lines is characteristic of iron. So that's called an emission spectrum because light is being emitted from these ionized atoms. The emission spectrum is a powerful analytical tool for identifying elements. So you basically look at the spectrum and then you match it with the known spectrums of different elements, and that can tell you what element is present in the discharge tube gas. Now, for some elements, it was possible to arrive at an empirical formula to describe the observed frequencies. So this was before people had any idea what's going on inside the atom. Why do we see this spectrum? Why do we see frequencies of a certain value in these spectrums, which vary from element to element? However, by looking at the hydrogen spectrum, simply by making measurements on its wavelength, a scientist by the name of Rydberg was able to come up with this formula, which describes the location of of the hydrogen spectrum. So if you fill the discharge tube with hydrogen gas, then the spectrum that is formed obeys this formula. What we have in this formula is the reciprocal of wavelength. So that's the wavelength of the observed line or the observed light of the spectrum. R is the Rydberg constant, which has a value of 1.097 times 10 raised to 7 per meter. NF and NI are two integers. They're positive integers, and the value of NI is always greater than the value of NF. This here is the spectrum of the hydrogen element, hydrogen gas. So what you see here is, this is like in this formula, Ni is an integer, a positive integer. So if Ni is equal to 1, then NF can have different possible values. I'm sorry, if NF is 1, then Ni can have a value of 2, which is over here. And this portion of the spectrum is called the Lyman series. Similarly, these lines that are observed in the spectrum correspond to what's called Bohr series, in which NF is 2, and then Ni has these values here. And notice the wavelength of Bohr series varies between 365 nanometers and 656 nanometers. Then we move on to the Paschen series, where NF has a value of 3 and Ni can be anything less than 3. Sorry, the greater than that. So if Ni is 3, if Ni is 6, NF would have to be less than that. So it can be 5, 4, 3, or 2, or 1. So essentially, various series have specific NF value. If NF is 1, the different possible values of Ni will give you what's called the Lyman series of lines of spectrum. If NF is 3, then we get Paschen series. If NF is 2, we get Bohr series. Now, the wavelengths for these series are such that the entire Lyman series falls in the ultraviolet portion of the electromagnetic spectrum. The entire Paschen series falls in the infrared area. Bohr series have some lines in the ultraviolet and then some that are visible. Let's look at problem number 8. Before we get to that problem, let me go back to this the spectrum here. So these ranges that are shown here. So the entire Lyman series falls in this range. And Lyman is characterized by NF being 1, and then Ni, which has to be greater than NF, can have values 2, 3, 4, 5, 6, 7, etc. And what you see here is the smallest Ni value, Ni equals 2. And then 3, 4, 5, 6 are all like bunched together here. In the Balmer series, NF is 2, which means Ni can be 3, 4, 5, 6, etc. This is Ni of 3, this is Ni of 4, and then 5, 6, etc. And then in Passion, NF is 3, and Ni therefore can be 4, 5, 6, etc. This is Ni equals 4, 5, 6, 7, 8, 9, and so on. So, so if you look at the spectrum, you will not be able to see the Lyman series because all of that is in the ultraviolet region. You won't be able to see Passion series. None of this will be visible because all of that is in the infrared. And then Balmer, you can see some of it, the one which have higher values of Ni. The lower ones, all of these, fall in the ultraviolet part of the spectrum. Okay, so problem 8. Problem 8 reads, find the wavelength of the third line in the Lyman series and identify the type of electromagnetic radiation. So first of all, we use the fact that in Lyman series, NF corresponds to 1. So we know NF is 1. And if NF is 1, then Ni can be 2, 3, 4, etc. We are interested in the third line in the Lyman series, which means Ni is 4. The first line would be Ni is 2, the second line would be Ni is 3, and then the third line would be Ni is 4, 1 plus 3. And then we use this equation here to calculate the wavelength. And remember that the right side is the reciprocal of wavelength. So when you calculate this, you have to take the reciprocal of your results to get what the wavelength is. So wavelength is all of this raised to -1. And then you plug in the values of Ni and Nf, and you get a value of 97.2 nanometers. And then if you look at the electromagnetic spectrum, you will find that this falls in the ultraviolet range. Now, as I said, this equation started out as being basically an empirical equation. You measure the wavelengths, and then try to fit the values into an equation. And this is what was arrived at. But there was no theoretical foundation to this equation. There was no model that existed, then why should the equation be the way it is? So that's the work that Bohr proposed. That's the work he did to come up with an explanation for the hydrogen spectrum. So he was able to derive the spectral equation for hydrogen atom by quantizing its energy or energy levels. So here's another instance of quantization. We've already seen how in Planck's model, atoms and molecules are considered to be oscillators, which oscillate at discrete frequencies, and they emit and absorb discrete frequencies also. And then we saw how light behaves like particles, which are like quanta of energy equal to h times the frequency energy of a photon. Now, here's another instance of quantization. You're basically saying that hydrogen atom can be in different energy states, but these energy states are discrete. It cannot have like any arbitrary energy. So each electronic orbit in an atom, including the hydrogen atom, has a certain energy value. Electrons can rise to a higher energy orbit by absorbing energy equal to the energy difference, or descend to a lower energy level by emitting energy, again, equal to the difference. So, for example, the various possible energy levels in a hydrogen atom could look something like this. So these are the discrete energy levels. So these could be however many electron volts or joules or whatever. So either the hydrogen atom can have this amount of energy, or it can have this amount of energy or this amount of energy, but nothing in between. And the electron in the hydrogen atom or the hydrogen atom itself can rise from this energy level to this. If you give it some amount of energy, it can go up to this level or to this level, but it can't stay anywhere in between them. So electrons can rise to a higher energy orbit by absorbing energy equal to the energy difference. So for example, let's say the energy of this was 2 joules, and the energy of this level is, say, 5 joules. So then if the hydrogen atom or the electron in the hydrogen atom is in this energy level, it can jump to the next one by absorbing 3 joules of energy. If you try to give it, say, 2 joules of energy, it won't take it. It's not interested because that doesn't do anything for it. The closest higher level that it has available to is 5 joules. So you will need to give it 3 joules of energy for this atom to go to a higher energy level. And once the atom goes up to a higher energy level, it stays there for a short period of time, and then it goes back here. And when it goes back down, it emits 3 joules of excess energy. So hydrogen atom can either absorb 3 joules of energy or emit 3 joules of energy, but nothing less than that. And these are numbers I'm just making up, so the actual values could be different, but this is just to show what the idea of quantization is and how a hydrogen atom can only accept certain amount of energy and not any random value. So electrons can rise to a higher energy orbit by absorbing energy equal to the energy difference, or descend to a lower energy level by emitting energy, again, equal to the difference. Now, energy is absorbed and emitted primarily as photons. So a hydrogen atom can either absorb photons or it can emit photons. And the hydrogen spectrum, or the spectrum of any element that we see coming out of discharge tube, is basically these photons which are emitted when the atom descends, when it falls from a higher energy level to a lower energy level. So if the energy changes by amount delta E, then the energy of absorbed or emitted photon is given by delta E equals HF. So this equation will determine the frequency of the absorbed or emitted light. So for example, going back to this, if 3 joules of energy is absorbed by hydrogen atom to go from here to here, then you can calculate the frequency of the photon that must be absorbed. You just set this equal to 3 and then figure out what F is. Similarly, if you wanted to calculate the energy released by hydrogen atom when it descends from 5 joule state to 2 joule state, you basically do the same thing. Delta E would be 3 and then figure out F. So delta E would be the initial energy state or the initial energy value minus the final energy value, change in energy. So this is sort of Bohr's reworking of the planetary model of the electron of the atom. So these circles that you see here are the different orbits, different possible orbits that the electron can be in. So E1 is the smallest energy level or the orbit with the smallest energy, and then E2, E3, E4, etc. So, and this is a good illustration of the quantization. These radii of the orbits have certain fixed values. You can't have an orbit which is between these. It's either this or this or this or this, but nothing in between. And this is an energy level diagram for the hydrogen atom. It's kind of showing the energy of these orbits. So the lowest possible energy corresponds to n equals 1, and that's this here. And this is called the ground state of the atom. So under normal circumstances, atoms are always in the ground state, the lowest possible energy state. And then there are possible higher energy states, n equals 2, 3, 4, etc. And these are called excited states. So when you have a hydrogen atom in its ground state over here, and then if you provide energy to it through photons, then it is possible for the hydrogen atom to absorb photons as long as they have the correct quantum of energy. So if a photon is able to take the hydrogen atom from n equal 1 to n equal 2 state, then it will absorb it. But if it's not enough, then it'll just ignore it, it won't accept it. And it's not just from 1 to 2. If you provide enough energy so that it can take you from n equals 1 to n equals 4, that jump is also possible. So, but it has to be the amount of energy you're giving it in order for it to be absorbed, it has to equal the difference between this energy state and one of these energy states. So in coming up with Bohr model, his mathematical model to describe the hydrogen atom, he made a few assumptions. He assumed, for example, that the orbits of the electron are circular in shape. And secondly, he assumed that the angular momentum of these orbital electrons is quantized. The symbol that we use for angular momentum, this is the circular counterpart of linear momentum. So when you have circular motion, the momentum of the object is called the angular momentum. And for a point particle with a mass me, which is mass of the electron, moving with the velocity v in a circular orbit of Rn, the angular momentum is mv, the linear momentum, times the radius of the orbit. So Bohr said that this angular momentum is quantized, meaning it can only have certain discrete values, and those values are given by this expression, nh over 2 pi, where n is a positive integer. So the different values of n correspond to different values of the radius of the orbit. So n equals 1 would correspond to the smallest orbit, n equals 2 bigger than that, n equals 3, etc. And v here is the orbital speed of the electron, the speed with which the electron moves in its circular orbit. V is the speed, Rn is the radius of the nth, Rn is the radius of the nth orbit. So angular momentum mvr can only be h over 2 pi, 2h over 2 pi, 3h over 2 pi, etc., but nothing in between. So that's basically the quantization of angular momentum. From these assumptions, Bohr was able to derive equations which matched experimental observations. So to follow along with Bohr's calculation, with his derivation of the equation, let's consider a hydrogenic atom. A hydrogenic atom is an atom that has only one electron, but it can have any number of protons. So Z protons and one electron. The simplest hydrogenic atom is hydrogen itself, which will have a Z of 1 because it has one proton. And then you get to helium. If you ionize, a singly ionized helium. Ordinarily, helium atom has 2 electrons. If you singly ionize it or remove one of those electrons, then it becomes a hydrogenic atom corresponding to Z equals 2, etc. And then you can go up the periodic table. So Bohr's derivation of the equation applies only to hydrogenic atoms, atoms with just one electron. So when the electron orbits around the nucleus, you might recall from mechanics that in order to have a sustained circular motion, you need some source of centripetal force. And centripetal force is the force that is always pointed towards the center of the circular orbit. So there has to be some source of this centripetal force. Like in the case of planets going around the sun, it's the gravitational attraction between the sun and the planets that provides the necessary centripetal force. In the case of an atom, remember, this is positively charged nucleus, this is negatively charged electron, and we know that opposite charges attract according to Coulomb's law, and the force between them is given by Coulomb force. So that's what provides the necessary centripetal force. Coulomb force is the source of the necessary centripetal force. Coulomb force between two charges. If you have charges Q1, Q2, separated by distance r. Then the Coulomb force is Q1, Q2 over r squared. And then there's a proportionality constant, K, the Coulomb constant. So that's the force between a charge Q1 and a charge Q2. So in this case, that force has to equal the needed centripetal force. And this is the equation for the centripetal force. If you have a mass me moving with a speed v along a circular orbit or circular path of radius r, then the centripetal force needed to sustain that motion is mv squared over r. So in this case, since the Coulomb force is providing that centripetal force, these two must be, this must equal that. As far as the charge is concerned here, we have Z protons in the nucleus. So the charge of the nucleus is Z times the elementary charge. Charge of a proton or an electron is E. The other charge, which is the electron in the orbit, is just E, the elementary charge. So this is, and Rn is the radius of the orbit. So basically all this boils down to this equation. And then if you simplify it, multiply the two E's, you get Kz E squared over Rn equals MEV squared. Now you can cancel this Rn with one of the powers of Rn here. And then from quantization of angular momentum equation, V is nh over 2 pi MERN. So this is the quantization of angular momentum equation. L equals, or MVR equals nh over 2 pi. So if you divide both sides by me times Rn, you get this equation. So V is nh over 2 pi MERN. So if you plug in this equation, the second equation here, into the first equation here, so replace the V by this expression, then that equation becomes this, Kz E squared over Rn equals all of that. And you can simplify this. For example, Rn here can cancel one of the Rn's here. And then Me here cancels one of the Me's here. So you end up with this. And then if you solve for Rn, multiply both sides by Rn and divide by Kz E squared, you get this equation. So the radius of the nth orbit in the hydrogen atom is n square h square over 4 pi square me, where me is the mass of the electron, k, the Coulomb constant, z, the number of protons in the nucleus, and then square of the elementary charge. I'm sorry, I shouldn't say it's the nth radius of the hydrogen atom, it's the nth radius of a hydrogenic atom which has Z protons. Now, if you take out the n squared and the Z part of this expression, the rest of it is a constant which we can represent by AB. A with a subscript of B, B for Bohr. So this equation Rn equals n squared over Z times AB represents a quantization of allowed orbits. So n, remember, is an integer. So the radius of the hydrogen atom can only have these discrete values corresponding to n equals 1, 2, 3, etc., but nothing in between. AB is this constant, and if you plug in the values, you get this number, 0.529 times 10 to the negative 10 meters. And this is called the Bohr radius. Bohr radius basically corresponds to the radius of the hydrogen atom, which has a Z of 1, in ground state, which has N of 1. So if you make N1 and Z1, then the radius of the orbit is just AB, and that's the Bohr radius. So that's the radius of the hydrogen atom in its ground state. And this value of the radius of the hydrogen atom in its ground state matches very well the experimentally measured size of the hydrogen atom. Now you might wonder, like, how do you know the size of the hydrogen atom or any atom? There are techniques. Most commonly used is X-ray spectroscopy, or you can observe these atoms under an electron microscope and you can measure their size. So these are the allowed electronic orbits in a hydrogen atom. R equals 1, R equals 2, 3, I'm sorry, N equals 1, N equals 2, N equals 3, etc. So these are the allowed electron orbits in hydrogen, and they have these radii, which were first calculated by Bohr and are given by that equation, Rn equals n squared over z AB. Okay, the next calculation that Bohr did after this is to calculate the energy of these electrons in these various discrete orbits. What is the energy that it has, the electron has, or the atom has? So we're going to consider the total energy of the electron, which is a sum of kinetic energy and potential energy. Assuming non-relativistic speeds, we can say that kinetic energy is half mv squared, and the potential energy of this would be QE times V, where V is the potential, electric potential at the location of the electron. The electric potential, if you have a system of two charges, the electric potential is given by KQ over R. If there are, let me draw this. So if this is the nucleus, this is the nucleus of charge Z E. There are Z protons, and each proton has a charge E. Then the electric potential at a distance Rn, distance between the nucleus and the nth orbit, is given by K. So V is KQ over R. So K times ZE over Rn. So that's what this is, this part of the equation. So the potential energy is this potential times whatever the charge you have. That is the potential energy of this charge. which comes out to QE times the potential, which is this. Now, you'll recall that in using these equations for potential or potential energy, you have to use the appropriate sign of the charge. Since we are talking about the potential energy of an electron, this would be negative. So the total energy is half me v squared minus kz qe squared over Rn. But mv squared over Rn is kz q squared over Rn squared. Centripetal force equals Coulomb force, from which mv squared is kz q squared over Rn. And then if you plug this into the equation for the energy, this is what you get. Kz qe squared over 2Rn minus kz qe squared over Rn. So if you subtract the second fraction from the first one, you get this. And then you plug in the value of the radius of the nth orbit that we derived earlier. That's the radius of the nth orbit. So if you plug that into the equation, that's what you get, kind of bulky, but you can simplify it to some extent. And then the energy of the nth orbit comes out to negative z squared over n squared times all of this. This entire expression in the parentheses is represented by E naught. So in terms of E naught, the energy of the nth orbit is negative z squared over n squared times E naught. E naught, basically this expression consists of constants, so you can plug in the values of mass of the electron, Coulomb constant, charge of the electron, and Planck's constant. And that turns out to have a value of 13.6 electron volts. And this represents the energy of the hydrogen atom in its ground state. So hydrogen atom, so Z would be 1, ground state, so N would be 1 as well. So it gives you the energy of the hydrogen atom in its ground state is negative 13.6 electron volts. A word about why the energy is negative. In order to have a closed, stable atom, its potential energy would have to be negative. If the potential energy or the total energy was positive, then the atom would be unstable. The electrons would just basically fly apart. So it's the negative value of the total energy that keeps the stability of the atom. Now, if in the ground state, the energy of the electron is 13.6 electron volts, what that means is if you want to ionize that atom, if you want to strip that atom of the electron, you would have to externally, you would have to provide somehow 13.6 electron volts of energy to remove that electron from the atom. So for hydrogen atoms, Z is 1, and therefore the various energy levels of the hydrogen atom are given by this equation, negative 13.6 over n squared. So again, n equals 1 would correspond to the ground state, and then the larger values of n are different excited states. The first excited state will have n equals 2, the second excited state will have n equals 3, and so on. So these are the different energy states or energy levels of the hydrogen atom. So that's the ground state at negative 13.6 electron volts. And then the electron of the hydrogen atom is typically in the ground state, but if you provided energy from the outside, it can make a jump to n equals 2 state, n equals 3 state, etc. And when it makes that jump from the ground state to one of the excited states, it stays there for a very short period of time, and then eventually it falls back. And then when it falls back, it emits that amount of energy, this energy difference, in the form of photons. And this is what we were talking about earlier. This constitutes the different series of the spectrum. So Lyman series is one in which the hydrogen atom ends up in the ground state, starting from any of these excited states. Balmer series is where the hydrogen atom ends up in n equal 2 state, starting from one of these, and then similarly Paschen and all that. And from that equation that I just showed you, we already saw that the ground state has an energy of negative 13.6 electron volts. And then if you plug in n equals 2, the value of the energy is negative 3.4, negative 1.5, etc. So if you wanted to ionize a hydrogen atom in n equals 2 state, you would have to provide 3.4 electron volts of energy to overcome that barrier. So as I was pointing out earlier, the fact that the total energy is negative, it implies that electrons are bound to the nucleus. Otherwise, if it was positive energy, it wouldn't be bound and you wouldn't have a stable atom. So in the ground state, as I was saying, 13.6 electron volts of energy is needed to ionize the hydrogen atom. Now, as n approaches infinity, as n becomes larger and larger, we are talking about orbits that are larger and larger. And starting from negative 13.6 electron volts for the ground state for n equals 1, as you increase the value of n, En approaches 0. So from here you can see as n approaches infinity, En would approach 0. And having a total energy of 0 basically means we now have a free electron. It's not bound to any atom. It's free to roam anywhere in the available space. When the atom falls from a higher to a lower energy state, the excess energy is emitted as a photon. If the difference in the initial and the final states is delta E, then a photon of frequency f, given by this equation, will be emitted. So HF would be equal to 13.6. Now, if you do EI minus EF, where EI and EF corresponds to these expressions, so EI would be negative 13.6 divided by the starting value of n, and then EF would be the final value of n. So this is what that ends up as. HF is equal to this. If you divide both sides by HC, then the equation becomes this. On the left side, the H's cancel out, and F over C is 1 over lambda. So 1 over lambda is 13.6 over HC times 1 over nf squared minus 1 over ni squared. And this constant, 13.6 over hc, if you plug in the values of Planck's constant and speed of light, has a value which is exactly equal to the Rydberg's constant. And you can see structurally this equation that Bohr derived is identical to the Rydberg's equation. So that sort of finally provides a theoretical foundation to an equation which was initially derived based on experimental observations without any underlying theory. So to recap the Bohr model of the hydrogen atom, there are two different quantizations going on. Energy turns out to be quantized because of the presence of that n, the integer n there. And the starting point of Bohr model was to assume that the angular momentum is quantized. So that was kind of the foundational for the derivation of the Bohr model. And then the third assumption in the Bohr model is that photons are emitted only when the atom makes a transition from one state, from a higher energy state to a lower energy state. So remember I was saying that how the problem with the Rutherford model was from the perspective of classical physics, if you have an accelerating charge, it should emit radiation and lose energy. But what Bohr said was atoms will lose energy or emit photons only when it makes a transition from a higher energy level to a lower energy level. So it doesn't do that on a continuous basis, but only when it makes a transition. So classically, we would expect a continuous emission because the charge is under acceleration, and the electron then would lose energy and spiral into the nucleus. But the presence of stable atoms suggests that inside an atom, these electrons, even though they're accelerating, they're not continuously losing energy. They lose energy only when the atom moves from a higher energy level to a lower energy. Bohr's model of the atom is called a semi-classical theory because even though it uses some ideas of quantum physics, it assumes that the circular orbits of the electrons are well defined, they have fixed radii and so forth. But this idea of fixed radii in the orbits was later discarded. It was found to be incorrect. So other than that drawback that Bohr model assumed, or it comes up with a well-defined circular orbit, and that not being an accurate description, other than that a drawback, the rest of the Bohr model, it correctly predicts the size of the atoms and the energy of the hydrogen and so forth, and the hydrogen spectrum. Another weak point of Bohr model is that it only works for hydrogenic atoms. If you have atoms with multi-electrons, then the theory sort of breaks down, or it doesn't work very well. You have to make certain corrections to the theory. Okay, let's look at problem number 21. A beryllium ion with a single electron denoted by Be3+, so it's a triply ionized atom, is in an excited state with radius the same as that of the ground state of hydrogen. In part A, we have to find the N for this beryllium ion. Beryllium, you can look up in the periodic table, has a Z of 4. There are 4 protons in the nucleus. So using the equation for the radius of the nth orbit, Rn is n squared over Z times AB. And we are told that it has the same radius as that of the ground state of hydrogen. So the radius of the ground state of hydrogen is just AB. N is 1 and Z is 1. So you set this expression equal to AB. And then AB cancels out on both sides, leaving you with n squared equals 4 or n equals 2. So that means this beryllium ion is in the first excited state, n equals 2. Okay, part B. How much energy in electron volts is needed to ionize the ion from this excited state? So we basically have to calculate the energy of this state. The equation for energy is negative Z squared over n squared times E naught, where E naught is 13.6. We found n to be 2, so we have a 2 squared in the denominator. And for a beryllium, Z is 4, so we have 4 squared upstairs here. You can do this calculation. It comes out to negative 54.4 electron volts. So the energy of this beryllium ion, triply ionized beryllium atom, in the first excited state is negative 54.4 electron volts. So that's how tightly this electron is bound to the beryllium ion, which means in order to release it, in order to ionize it, you would have to provide this much energy. So 54.4 electron volts of energy is required to ionize this. Okay, we will continue with 30.4 in the next video.